section 2.4, we are going to review the different, the parent functions, the basic functions, and the graphs that we should picture in our heads by just looking at function. All right, that's number one. And number two, we're going to graph what we call piecewise defined functions, which are functions that are defined in different pieces for different intervals, and therefore in a same graph we will have, for instance, a portion of a graph of a parabola, then maybe a line, then maybe a radical function. Well, there's many crazy things that we're going to do with piecewise functions. All right, well, in the meantime, let's review all the different functions. Well, so number one, the constant function. By the way, these pages 88 and 89, I don't think they're accurate with our textbook because I believe I got this from a different resource. So don't go to that page. Or maybe yes, just in case. I don't know. So the constant function, that looks like f of x equals to b. Or, you know, as examples, well, I can give you something like, I don't know, f of x equals to 3, for instance, g of x equals to 7, h of x equals to -2. And what these graphs do, it's going to give us simply horizontal lines at the y values of 3, 7, and -2. Let's go to the graphing calculator to see those. Okay, what did I say? 3, 7, and -2. So 3, I'm going to go 7 and the -2, all right? So if we graph them, that's going to give us the 3 lines right here, 3 horizontal lines, where actually those lines have a y-intercept but no x-intercept. Well, unless it's the line y equals to 0, which intercepts or overlaps with all of the x values and only crosses the y value of y equals to 0. So those are examples, and of course you can put your favorite number, 9, 17. So the thing here, for instance, let me clear this. Okay, clear, and clear. Well, for instance, you want to see y equals to 17, for instance. If we click graph, we won't be able to see it, and the reason to this is because our ratio, or rather our scaling, our window rather, it's -10 to +10 in the x-axis to -10 to +10 along the y-axis. So 17 is not there. Well, that can be easily fixed if we change the window. And I would like to do maybe from I'm going to do -1 only. Let me delete the 0. I'm going to go to 19, for instance. And I'm going to go with a scale of 1. So that's going to change. Oh no, that's the x. Never mind. So that should have been, okay, -10. -10 to 10. And it's the y, the one I want to change. The y equals to -1. Let me delete that 0. Let me change that 1 to, or that 0 to a 9 to make it a 19. And then, well, then you will be able to see this, your line y equals to 17, because the largest y value that we will be able to see after adjusting the window is 19. All right? And well, you can scale this however you want. In this case, the what's it called, the x scale, y scale. Well, I did it by 1 so that each mark represents 1 integer. You can make it, say, y min, y max, and scale 0.5, for instance. And if we click graph, well, you will see a lot of marks, each of them representing a 1/2 or a 0.5. So you will see 1, 2, every 2 will be 1 integer. And well, you do these kinds of things about adjusting the window when you want to graph irregular functions. You know what I mean by irregular functions? That for for weird values that are not like integers when you want to do other kinds of estimations, for instance. But for the most part, we're going to go with nice integer values for our purpose here. Right? So those were a couple of examples on how to graph these horizontal lines and how to do some extra in case you can see the one you want to see in a negative 10 to 10 to negative 10 to 10 window. Now, if you want to go back to the original window, what you might want to do, click zoom and then click the number 6, which is Z standard, and the standard is the negative 10 to 10 in the x direction and the negative 10 to positive 10 along the y direction, or the y-axis rather, not direction, axis. Let's see, what's next? Okay, so those were examples of the constant function. Well, the identity function. What's the identity function? That's the graph of a line with slope equals to 1 and y-intercept equal to 0. And the reason why we call it the identity function, that's because if you make a table of values x, y, what happens if you give the following values: negative 3, negative 2, negative 1, 0, 1, and 2? Well, plug in those values for x. Well, what are you going to get? The same values, right? Negative 3, negative 2, negative 1, 0, 1, and 2. You get the exact same values of y for x. Because essentially, f of x right here, it's the same as saying y equals to x. I mean, the y and the x values are the same. And well, the next example, the next type of function is what we usually call the square function or parabola. That's or quadratic function, right? But this is just like the baby case of a square function. A more general case. So, a more general case will be some function f of x of the form ax squared plus bx plus c. That is a quadratic function that contains not only the square term but also all the terms that are lower in degree than the square. That is the linear term or the term to the first power, and the constant term, which technically is the term the term of 0 degree. What do we mean by 0 degree? I mean, this is a 2, this is a 1. You can call this c as cx to the 0, but x to the 0 equals to 1. 1 times c is simply c. So that's why, in a way, in spirit, that c has an x being multiplied with, however, of a power 0. And well, of course, we can come up with many examples of square functions. However, we're going to get into those examples in the next section when we'll look at at the transformations, the shiftings. You know, I could make up a lot of them, like, I don't know, f of x equals to x squared minus 1, g of x equals to x squared minus 7, for instance. H of x maybe equals negative 3x squared plus 4, you know. Play with the coefficients and their signs, and we'll see in the next section actually what those numbers, what those signs will make to the parent graph. In the meantime, it's about to get familiar with them. And well, how do we get to graph that equation? Well, all we do is go to the y equals symbol. If you have anything else clear, like I had that 17, and I'm gonna go and type the letter x, the variable x, and well, there's a couple of ways to write the second power in this case. Number one, you have a key for the square, or type the x, then power and 2. Either way should give you the same thing. All right. And well, so just click on graph, and you should see the graph right here. Now, if you're curious about the y values or the function values, you can click second graph to reach out a table. And that's going to give you a table of values for the function. Instead of doing them by hand, you can do that. I mean, all it's going to do, I'm pretty sure you recognize these numbers, 0, 1, 4, 9, 16, 25, 36, and so on. These numbers are the perfect squares, right? That's because, well, our function is a square function, all right? And it's outputting the perfect squares, all right? So, well, that's one example. That's another example. The next function, the cubic. Well, the cubic, which looks like this, looks like it has one of its tails going down and one of the other and the other tail going up. It's like you. It's as if you did this. If you reflected this part, the first tail of the square function, and think of the x-axis as a mirror, and instead reflect it like this. All right. Now, let's compare these two functions. These two functions, the square function and the cubic function. Let's think of their properties, the ones that we discussed last time. Think about the symmetry of the two by looking at these two graphs, and tell me about their properties. What about the square function? What can you say about it? What did you notice about the square function?
It's only going in one direction.
What is that again?
It's only going in one direction.
It's going in one direction towards the positive infinity, all right? It's going in one direction. What else?
It's easy to guess which one the next one is.
It's easy to guess. Well, that's because you know the perfect squares, right? So you know the trend. You have memorized some of the values. Well, that's correct. What else? What else about this one? What do you notice of interesting about it?
That it's even. I think it's an even function.
How do we know it's even?
It's through the origin.
Passes through the origin. Well, the cubic function also passes through the origin. The square function also contains the origin. The cube root function also contains the origin, and I don't think all of those are even functions. So there's another. Okay, you're right. The function is even, but that's not the reason why it's even. Because what? A variation.
Mirrors.
Okay, mirrors. So now we need to be more specific about how it mirrors. It's symmetric. Symmetric about the x-axis. Well, if this were our mirror here, then this graph should be reflected right like this, right? So okay. So the symmetry is correct. Okay, number one. Number one is even, right? And then that's because it's symmetric. But let's be more specific about its symmetry.
Scott, I mean, you said like that it's symmetrical about the y-axis.
The y-axis, right? It's symmetric about the y-axis. That is correct, all right? It's even, it's symmetric about the y-axis, etc. All right, let's compare it with y equals x to the third power, or y equals x cubed. That is the cubic function. All right. What do you notice about? Let's think of the same properties.
So this one would be odd because it's symmetrical about the origin.
Exactly. So in this case, it's odd because it's symmetric about the origin. All right. What about the identity function? Let's talk about its properties also.
It would be the same as the cubic.
Odd.
Odd because it's symmetrical about the origin.
Yep. This point right here is reflected over there about the origin. And what about the constant function? Would that be even or odd? Even. All right. All right. And well, in this case, you might be thinking, well, vertical line test. Well, all of these functions pass the vertical line test. If any of these functions didn't pass the vertical line test, then we wouldn't be able to express them as f of x, that is, as functions. So, in fact, just as equations. All right. Let's see the square root function. The square root function. Oh, number one, the cubic function. How do we graph, or rather, how do we type the cubic function on our graphing calculator? Number one, that'll be x, of course, the variable, and you have two options. Number one, because here we don't have a key for the cubic, you might want to do it manually, like the power and then the 3. And then you will see the graph and see how it looks like the one we have in our notes. So that's one way. Actually, there's a built-in function to cube a quantity. How do we get it? Well, let me quit here and let me go back to y equals. Let me clear everything there, and that'll be, well, x. And instead of erasing, I'm going to go math. I'm going to click math, and you will have the number 3 right here, which has a 3, actually, a very tiny 3 that looks actually like a power. Let me do that part. Let me do 3 and then click enter, and that's a second way to get the cubic function. And then click graph, and you should be seeing the same thing. All right? Nothing different. Well, we already discussed everything about this function, evenness and oddness. Well, in this case, it's odd. Let's move on to the next one. All right, so let's see. Square root function f of x equals the square root of x. Okay. So in this case, although you can pretty much use your favorite value of x except the negative values, because if you try and evaluate the square root of a negative number, you will find out that it's not a real number. That's something we covered in our radicals review, right? So the domain of a square root function again is 0 or greater than 0. That is greater than or equal to 0. And well, notice here we have key points. We don't have a bunch of points like here we would have like 1, 1, 2, 4, 3, 9, 4, 16. No, in this case we have 1, 1. Otherwise, if I did the 2, it would be 2 square root of 2, which is not a it's not a rational number, it's an irrational number. And in fact, if you do it in your calculator, you would get decimals. Actually, let me show you how to see that table again. Well, number one, y equals, okay, let me clear everything here. So now there's a couple of ways to get, well, I don't think there's a couple. Let me see. No, let's just do one. Okay. So the radical, the square root, it's going to be the second function of the square function here. Notice how you have the radical symbol very, very tiny here. That means because it's in blue, you need to press the second function and then the x squared button to actually spawn the radical symbol here. And then just type the variable x. All right, let's click graph, and that's going to give us very similar. It's somewhat similar. It looks a little smashed compared to what we have in our notes. And the reason to that is because of the aspect ratio of our graphing calculator. It's not perfect. The screen is not perfectly square. It's actually more rectangular. In fact, if you see the marks for the x-axis, they're not evenly spaced with respect to marks along the y-axis. So that's why we may see this graphs a little bit different. In fact, if you try to graph a circle, for instance, it's not going to look like a circle. It's going to look like an ellipse, like an oval, actually. So just so you don't get a little confused when you're looking at the graphs having one shape on paper versus having a slightly different shape in our graphing calculator. All right. What's next? Oh, okay. I was talking about the values, right? So you might want to click second in table because it's in blue. And we'll see how you're going to see a lot of decimal values except for the x values that we know they are perfect squares because those numbers have a perfect square root. Like in this case, the square root of 0, which is 0, the square root of 1, which is 1, and then the square root of 4, which is 2, and then all the numbers between that are greater than 4 and less than 9 will output decimals because those are numbers that do not have an exact square root. And then the next perfect square is it's 9, and then keep going. You can just use the arrow, go down, and you will get pretty much an infinite table. You can click forever and you will get all of the values of x, of course, that are in the domain. Well, the next is 16. Keep going, keep scrolling until you see 24, 25. That's 5. What happens if you go instead up? See how you're going to get error if you type a negative number? That's because the square root of a negative number is error. All right? All right. So let's see. Let's keep going. Let's have a look. Let's analyze this graph and think of the properties in a similar way we did for the cube root, the square root, and all that. What can you say about it? Is there any symmetry?
It can only be positive.
It can only be positive, right? Function values are always positive. What else? Even, odd, neither even or odd.
It is a function, but it would be neither even nor odd.
Neither even nor odd, right? There's no symmetry. I mean, unless we had another tail right here, well, it would be symmetric about the y-axis, and therefore it would be, would that be even, right? Or if we had this tail like this, then it would be odd, right? But it's not the case. So in this case, neither even nor odd. All right. All right, let's have a look at the next type of function. F of x equals the cube root of x. And well, we have a picture of it. And I think from the picture you can already tell a little bit more about its properties. Of course, we have some of the key points. Well, not all of them, only the ones that are values that are perfect cubes, like in this case the cube root of 8, which is 2, the cube root of 1, which is 1, etc. All right, cube root of 0, which is also 0, cube root of -1, that's -1, cube root of -8 is -2 again. Recall from our review about radicals that we can take the cube root or the odd root, not just the cube root, any odd root of a negative number like the 5th root, 7th root, 9th root, etc. And then from here, well, let's see if we can determine some of its properties. What about even, odd, or neither? Odd? Well, how do we know it's odd, by the way?
It's symmetric on About the origin.
About the origin, because if you look at this point, for instance, 8, comma 2, both coordinates x and y, the x and the y coordinate are negative. That means they are symmetric about the origin. So the origin in this case is the mirror, and actually what we get both values negative. All right. So again, okay, let's write it down. So that's odd, symmetric, about the origin. All right. How do we graph the cube root function? Well, there's a couple of ways to do that. So, okay, let me let me go back to y equals, let me clear. Well, in this case, the only radical function that we have in our calculator in blue, that's the square root. However, there's two different ways to type the cube root. One way is, number one, go to math, and then go number 4. Number 4, it's actually cube root. Click enter and just type the letter x, which is the variable, and then graph. And we can see again a somewhat similar graph. And when I say somewhat similar, again, that's because of the aspect ratio of a graphing calculator screen in this case. So it's just going to look a little smashed. That's the only thing. All right. The other way to write it down, well, check this out. First of all, here is where we need to go back and review our properties of radicals, which we did a lot of them. Recall that the cube root of x, using the property nth root of x to the m, it's the same as saying x to the m divided by n. Again, the index of the radical tells us the denominator of the the rational exponent. So in this case, we can rewrite the cube root of x as x to the 1/3. All right? And, well, let's go to the calculator and type. Let me clear. So that'll be x raised. Well, in some cases, guys, in the newest calculators, the minute you do the exponent, the raising to a power, it's going to actually the interface is just going to it's going to flash for the exponent, and all you do is 1 divided by 3. All right, click graph, and you will see the same graph. However, older versions of the graphs or the graphing calculators will require you to literally type all these commands like x, type it, open parentheses, 1 divided by 3. I don't think I have the older interface. Let me see if there's a way. I remember, no, it's the TI-84 plus. Okay, let me see if I can do it here. Okay, so y, so x raised to, no, it's still gonna do the power anyway. I don't think there's a, no. Anyway, let me change my version back to the CE. Oh, come on, it's not changing. Anyway, there you go. So you may need to do that for the older calculators. All right, and let's see what's next. The reciprocal function. 1 over x. 1 over x, well, in this case, that looks like this. It has essentially two tails. One tail or one curve, rather, on the third quadrant, and another one on the first quadrant. And what we do is calculate the reciprocal values. For instance, f of x equals to 1 over x. For x equals to 2, for instance, we're going to get the reciprocal of 2, which is 1/2 f of 3. That'll give us the reciprocal of 3, which is 1 over 3 or 1/3, etc., etc. All right? And well, to get these graphs, Let's see, y equals to, let me clear all this, 1 over x. So 1 over x, and then graph. And this is what we're going to see. Now, here is the thing. Number one, our graphing calculators, yes, they're very smart devices. I'm not going to lie. Because they can calculate pretty complicated results. However, they're not that smart. And here is where we should be smarter than the graphing calculators. Number one, the number one issue with the calculator is it's not going to go all the way up or all the way down along the y-axis the same way it does. It does it for the x-axis. Number two, something we need to keep in mind here is that notice, well, suppose that we are walking along this graph. So we walk and walk, and what's gonna happen when we approach zero? Where are we gonna go? We're just gonna fall into negative infinity, right? And then we would have to jump to positive infinity to keep walking and keep going with the same road here, right? So there is a problem with this jump discontinuity. Well, it's not called a jump discontinuity. It's what we call a vertical asymptote. All right, right here we have a vertical asymptote, and also we have a horizontal asymptote. What are those asymptotes? So those asymptotes you can think of borderlines. You can think of borderlines for which graphs, yes. This means the graph is going to keep going forever, and it's going to approach zero. All right, let me keep drawing this asymptote. And it's just going to keep going and getting close to zero, but actually never ever touching that zero. Right? That's what we call the asymptotic behavior of a function. And it happens the same way in the vertical direction. If we keep going up, we have the same asymptotic behavior here. But notice how this graph never touches the y value or the x value of x equals 0. Same in this direction. If we keep drawing this vertical asymptote, that is, it just keeps going down and down, getting closer, but again, never ever touching that value of x. In fact, you can think another way to think of these asymptotes, it's trying to repel the function as much as possible. All right? Well, we're not going to really get into all of these details for now, but we will later when we get into the transformations. What else? Maybe, the transformations. You'll see how those transformations, horizontal and vertical, also change the location of of those asymptotes as well. All right. So number one, let's think about this function, even or odd. F of x equals 1 over x. Odd? Do we agree with odd? So yeah, do you see the symmetry here about the origin? Yep, odd. Symmetric about the origin. There's one that it's not here in our function repertoire here. So let me do it by hand. It's also a reciprocal function. Well, let me do it here. Yes, here. No. The reciprocal function, but instead of f of x equals to 1 over x, let me do f of x equals to 1 over x squared. All right, let me do f of x equals 1 over x squared. All right, the graph of f of x equals to 1 over x squared, it's going to look a lot like following. So number one, let me do the axis first. And instead of having the two curves or the two tails, one pointing negative, one pointing positive, actually both point in the positive direction like this. Right? And well, let's see. Number one, by looking at this graph, even or odd?
Even.
Even? How so? Why so?
Symmetric about the y-axis.
So even. And that's symmetric about the y-axis. All right. Now let's have a look at this function using the graphing calculator. Well, so that's y equals 1 over x. Let me just take advantage of this already typed and change it. Oh, come on, let me clear it. 1 divided by x quantity squared. And that'll be, okay, let's click the graph and we'll see those two graphs actually pointing up to positive infinity. All right. So this is what happens when we, with the reciprocal functions. We're going to have a couple of reciprocal functions for which the denominator power is an even. So let's see what happens if I add more. Instead of 1 over x to the second, 1 over x to the, what's the next even number? 4, 1 over x to the, oh, hold on, that's clear. 1 over x raised to the 6th power. So all we're going to get is just a very similar graph, however slightly smashed towards the origin. And then the same, in a similar way, we can also do the 1 over x, delete, and I'm going to change this 4 with the next odd number, that is 3. Come on, there we go. And let me make this 5. So we're going to see the graph, actually the two tails pointing, one positive, one negative, with different smashing factors, if we will. All right. But again, we're going to get into detail about this type of graphs later when we discuss the different transformations. Coming back to the notes, and there's another one called the greatest integer function, which is usually also known as the step function or the staircase function. Well, I think you can see why do we call it like that, all right? And usually we graph the greatest integer that is between, well, that it's actually greater than a given, for instance, a given x value, for instance. So if I wanted to plot the greatest integer of, say, 2.1, so the greatest integer that is larger than 2.1, what is, or not larger, rather lower than 2.1, what is that greatest integer? That is the greatest integer smaller than 2.1. And we can see 2.1 was the y value for 2.1. From the graph, what's the y value? 2, all right. What about the greatest integer of 2.9? So if we go to 2.9, what is the y value? Also 2, right? Now if we go to 3, well, that actually, it goes all the way to 3 because that's a new integer, that's 3, and it's going to notice how we have a full bubble in this case. It's not the most common type of graph that we work with. However, you will get to use it maybe, well, not maybe, but actually you will get to see it when you get to calculus. All right? These notes. All right, analyzing a piecewise defined function. So when a function is defined by different equations on different parts of its domain, it's called a piecewise defined function. Well, this is how piecewise defined functions are going to look like. So we will still have the f of x notation, or g of x, or h of x. However, you will have curly braces. You will have 1, 2, or maybe 3, 4, 5, 10 different equations alongside actually, rather, you will see these inequalities. So in this case, well, how about we call this the functions rather, and these are called the conditions. So these are the conditions because, well, so this is what we're going to do. Let me highlight each of the functions. Let me highlight each of the function along with its condition with one color. Okay, let me use this color for the first part of the function. Let me use a different one for the second one. So this is what I would like to do. I'm going to go the table approach. We're going to make a table of values for each of the functions. So I'm going to do one table for number one, for the first part, the part in green. Okay, so x. And well, usually the way we graph the equations from the beginning of the semester, well, yes, the technique here is to just input values of x. However, in this case, we can't just give any values of x at our discretion here because we have a condition. So that means x plus 3 under the condition that x is less than negative 2. What does that mean? What could that mean? That x less than negative 2? So what are those values of x that are less than negative 2? All right. Could you give some examples? Negative 3. What about another one? Let's keep going. Negative 4. Negative 5. Negative 6, etc. Okay, so let's make a table. Well, check this out. I'm going to include the negative 2, even though we're not supposed to, because, well, here it says x less than negative 2, not less than or equal negative 2. If it says x less than or equal negative 2, then, well, you'll see what happens. So I'm going to include it anyway. So negative 2, I'm going to do negative 3, negative 4. I'm not going to do too many, just a couple. All right, let's plug them in the original function, the part in green only. Negative 2. Okay, y equals to x plus 3. Negative 2 plus 3, that equals to 1. Negative 3 plus 3, that equals to 0. And what else? Negative 4 plus 3 equals to negative 1. All right? So here is the thing. Even though I plugged in the value of negative 2, but because in this case is less than, this will be, number 1, this is going to give us a set of order pairs x, y. It would be a good idea to have a third column for order pairs. Those are going to look like negative 2, 1, negative 3, 0, and negative 4, negative 1. All right? However, in this case, this will be a whole, an open circle. That's because in this case, where x equals to negative 2, we just have it as less than. So that will be a whole at the point negative 2, comma 1. Let me go about it. So negative 2, comma 1, open circle. And then let's see, negative 3, comma 0. That's going to be a solid point. Negative 4, comma negative 1. And of course, I mean, we don't have to go all the way. We don't have to do more computations. We can just draw that part of the graph. All right, let's go ahead and do it. And we'll indicate with an arrow that this graph is going forever in the negative direction towards the left and down. All right, so we are done with the first part of the piecewise function. Let's do the second part. The second part, so let's make another table. X and then negative 2, x minus 3. All right, and well, in this case, yes, negative 2x minus 3, although we can plug in pretty much every single value of x, because we don't have any radicals, we don't have any, what's it called? We don't have any x's in the denominator that can cause a 0 in the denominator or the like. But the thing, we still have a condition. So let's pay attention to the condition x greater than x equals x greater than or equal to negative 2. So that second condition is telling us that we are only allowed to evaluate that second part of the function for values that are x greater than or equal to 2, that is, or I mean negative 2. Negative 2, for instance, that's 1. Negative 1. 0. I'm not going to do too many of them. All right? Okay. So let's evaluate this. That'll be negative 2 times negative 2 minus 3. And that equals to negative times a negative is 4 minus 3. That equals to 1. And then negative 2 times negative 1 minus 3. That equals to positive 2 minus 3. That's negative 1. And then negative 2 times 0 minus 3. So that's 0 minus 3, which equals to negative 3. Now, this is going to give us a few order pairs to plot. That is negative 2, 1. And then negative 1, negative 1. And 0, negative 3. Right? 0, negative 3. So let's plot those points. However, check this out. So in this case, because the negative 2 it's allowed to be on the graph by the condition, because it says it's greater than or equal. The equal means including. This is not going to be a whole anymore. This is just going to be a solid point, just like the other points. And that's going to be, well, let me use the same color. Well, that's going to be the point negative 2 comma 1. Actually, that hole gets filled by the solid point from the second part of the piecewise function. And then the next point, that is negative 1, negative 1. And then 0, negative 3. And then just draw a graph going all the way to negative infinity. All right, we don't have to plot infinitely many points. All right, and well, in this case, well, I'm using two different colors so you can see how do we construct the piecewise function, rather how do we plot it using one color for one different piece. All right, and then let's see. Oh, they're asking us to evaluate some function values, f of negative 2. All right, here we need to be careful about how we, or where, in which of the pieces can we evaluate f of negative 2. So f of negative 2 will be allowed to be evaluated only at either the green one or the yellow one. All right, which of the two allows the negative 2? Which one? The second one, right? Because it says x greater than or equal to negative 2. All right? Yes. So in this case, on the second one, let me use the same color. That'll be, okay, negative 2 times negative 2 minus 3. All right, that's 4 minus 3, which equals to 1. Well, that's the solid point we had over here. All right. Okay, so these conditions and these different pieces of the of a function. Think of trying to get into a club, you know? You're not allowed to be in clubs if you're not 21 or older, right? Okay, so the yellow function here represents allowance to be in a club. All right, well, let's pretend this -2 is a 21. That is, are you 20 equal to 21 or greater? Well, you're in. But if you're not, no, you get out of the club. That is the green function in a way. So that's one way to interpret these conditions to graph the different functions. Now, f of 4. Is 4 allowed in the yellow one or the green one?
I don't understand where you got the -4 and the -3.
No, it's equal sign.
Oh,
Yep. But I guess yeah, it's an equal. All right, what about 4? Is 4 allowed in the green one or the yellow one?
Yellow.
Yellow? Yellow. In fact, you can see it in the graph. 4, x equals to 4, belongs to the yellow section. So that is -2 times 4, and then -3. That equals to -8 minus 3, rather, which equals to -11. And lastly, f of -4. Okay, -4 is -4 in the green section or the yellow section? In the green section. So we're going to use the green function. Let me change color. That is x plus 3. That is -4 plus 3, which equals -1. Right? Okay, let's find the domain of this function from the graph. And well, we have done a lot of this since the beginning of the semester. Let's see. I'll let you guys work on the domain and the range for it. So to find the domain of this function from the graph, again, keep in mind that every time we have functions that are represented with arrows to indicate that the graph continues on and on, well, depending on the direction, we can always break them up in accordance with the x component or a y component. So this arrow right here indicates that it's going towards the right at the same time that it's going down. Also, this arrow here is indicating that it's going to the left in the same way that it's going down. So that's going to help us see the scanning and how are we going to see the domain. Well, scanning from left to right, we can see that the domain, it's all real numbers, -infinity to +infinity, and using set notation x such that x belongs to the set of all real numbers. And for the range, again, we need to scan the graph from bottom to top. Now again, these two arrows broken up from their corresponding origin of the arrows, they're going down. That means they're going all the way down to -infinity, but in fact, since we're scanning from bottom to top, we're not saying that they're going down to -infinity. Rather, we say that we're coming from -infinity, but in this case, we will reach a maximum value, right? Is it going to go all the way to +infinity?
No.
What's the max value that we get? All right. So in this case, it's going to go between -infinity to +1, including the 1, because in this case it's a solid point. All right, it's a solid point. Yes.
so when we first wrote it out, wasn't it an empty circle?
It was an empty circle, but it is that second function that actually fills in that open circle. All right. I mean, don't get me wrong. There could be cases in which the second function doesn't fill in that open circle, either because it's also not a full circle, that is, it's also a greater than only or without the equal, or maybe it's just shifted up one way or another, for which we will see a couple of examples later. All right. And well, yes, okay, the range will be y such that simply y is less than, in this case, less than or equal to 1. All right. Okay, how about we do a little bit more analysis of this? Well, even though it's not typed right here, let's see. Let me call it D. Increasing. Okay, what is the interval in which the function is increasing?
Isn't the same as
Negative infinity to 1. Well, 1, in this case, well, we're talking about just the x direction, so on the graph, all right? Just negative 7? Well, keep in mind that the graph has an arrow that indicates goes forever. To negative 2, right? Increasing over the interval negative infinity to negative 2. And again, keep in mind the endpoints are exclusive, because if you include the point, the solid point, well, think of trying to stand on the cusp of that hill right there. Actually, there's many directions from there. Actually, you can go down or one way or the other. Letter E. Decreasing. What's the interval in which the function is decreasing? Yes?
It would be bracket 1.
1?
Positive infinity.
But why would it be 1?
Or, sorry, negative.
Negative 2, right? Negative 2. But in this case, parentheses, because we don't include the value for intervals increasing, decreasing, all the way to infinity. All right? Now let's see. Letter F. Even, odd. What do you think of this one? Is this even? Is this odd? Yes?
How is it positive equation?
Because again, from 2 all the way, what is that arrow indicating? That it's going all the way to positive infinity, right? And it's just going down, decreasing. But it's about the x-axis only. So the interval, the x values at which it increases and the x values at which it decreases. Even, before the even and odd. No, not the even and odd, not yet. Let me do relative, okay, relative, max or min. Which one do we have? Do we have a maximum value? Do we have a minimum value? And since it's only one, it's both relative and absolute. And what is that? At which value of x, by the way?
32.
At x equals to negative 2, we have a maximum of what's the y value? It's 1, right? So no minimum, right? No minimum. And lastly, yes, let's now do the the even and odd. Even, odd, or neither. So what would we say about it? We say neither, right? Do we all agree with neither? How so? Why so? Number 1, check for symmetry about the y-axis. Do you see the y-axis acting as a mirror in this case? I don't think it is. What about the origin? Same. So no symmetry. No symmetry at all. Let's change color here. All right. So that's one example. We got a lot of information. Let's do another one. All right. Now we need to be very careful with the conditions for this couple of functions. That is, the function comprised by two parts again, 2 minus x and the square root of x. One has a very interesting condition. Let's see. All right. So let me highlight them first. Let me use green for the first one, and let me use yellow for the second one. All right, so I'm going to make a table for each. All right. However, check this out. Notice the restriction for the 2 minus x. Although the 2 minus x pretty much has an unrestricted domain, it's a linear function. Well, that condition just next to it is telling us that we can only input values that go between -3, actually including the -3 because it has a less than or equal, and all the way up to +1, however, without including the 1 because we have the less than only. If we had the, the equal part here, then we would include it and it would look solid. So now, not in this case, and let me write a couple of notes. Including, that is solid. Excluding, that means not solid but actually open circle or whole, right? And in this case, all x's that are greater than 1 without including the 1, that means another whole. Excluding, excluding represented by a whole. Okay, let's make a table for each of the functions. So x's, and well, for x I cannot just evaluate it at my favorite values of x. I'm going to do all the values that go between -3 and 1. Well, actually, I'm going to skip some of them too because I don't want to spend too much time doing a lot of them. I'm going to do -3. You know what? Let's do all of them. -3, -2, -1, 0, 1, and 2. I mean, just 1. I can't plug in the 2 here. Okay, so y equals to 2 minus x. Okay, so what do we do here? So 2 minus -3, 2 minus -2, 2 minus -1, 2 minus 0, and 2 minus 1. Okay, let's simplify this calculation. So that'll be that minus in the front turns it into a plus. So 2 plus 3 equals to 5. 2 plus 2 equals to 4. 2 plus 1 equals to 3. 2 minus 0 equals to just 2. And 2 minus 1 equals to 1. Okay, but again, every time you create a table of values, keep in mind that the x's and the y values that we obtain form order pairs that we're going to use to plot the graphs of these functions. That is xy, that is -3, 5, -2, 4, -1, 3, 0, 2, 1, 1. All right, pretty much all of these points are going to be solid. Solid for x equals to -3 because it includes the equal. However, the only point that will not be solid actually will be represented by an open circle. By a whole will be the one related to x equals to 1 because it just says x less than 1. We don't include that one. All right, so solid solid, and whole. All right, let's go about it. Okay, so the point -3, comma 5. That's this point. -2, comma 4, -1, comma 3, 0, comma 2, and 1, 1. That's where we're going to draw the hole. All right. Okay, that's just going to be the first part of the piecewise function. All right. So we're done essentially with the first piece. Let's do the second one. So x y equals the square root of x. And well, again, here is where we need to be careful with the values that we choose for x. You might want to choose values, smart numbers, smart values, that is, values that you can take the square root of them, that you get an exact number. I mean, of course you can plug in, well, we can plug in numbers that are greater than 1, but not 1. I'm still going to do the 1 because that's still going to be represented with a whole. All right? So here is the thing. We can plug in 1, 2, 3, 4, 5, etc. Your favorite number. But again, keep in mind that the square root of 2, the square root of 3 are going to give you decimal values. So just go with perfect squares. So going with perfect squares, I'm going to do 1, 4, what else? 9. Just these 3. All right, so that is y equals the square root of 1, square root of 1 equals to 1, the square root of 4 equals to 2, square root of 3 equals to 3. That's going to give us a few order pairs. The order pair 1, comma 1, the order pair 4, comma 2, and the order pair 9, comma 3. Okay, those are the order pairs of the form xy. All right, so again, because of the condition x greater than 1, that point 1, comma 1 will still be a whole. So if we had greater than or equal to 1 otherwise, well, then it would have been a solid point like in the previous example. All right, so all of the remaining points are going to be solid, etc. We don't need to write down too many. So let me use yellow for this. And well, again, let me do an open circle here, overlapping with the green one here. And then that's 1, 1, and then 4, 2, and then 9, comma 3. And that's going to give us, something like this, maybe. Like this, all right? And that's in this case with an arrow. Notice the arrow here, but no arrow on the left side of the graph, all right? Okay, so that's the graph of this piecewise function. That's one linear part and one radical part. All right, now let's answer some of the questions. So here, okay, here the borderline value, you can think of a borderline value. So if the number is greater than +1, well, that is admitted in the yellow section. If the number is smaller than 1 but actually has to be greater than or equal to -3 to be admitted in the green section. So this function has more restrictions than the one we did before, and we need to be very careful when interpreting those those restrictions, those conditions. All right. Okay, so let's evaluate f of -2. Now, the x value of -2, is it admitted in the yellow region or the green region? Okay, what is the value of f of -2? Okay, you can use the graph or use the function that we have, 2 minus -2, which is 2 plus 2, which equals to 4. And then next, f of 4. Where is the number 4 admitted? Is it in the green region or the yellow region? Yellow. All right, so let's take the square root of 4. That is, so notice I'm using the function related to the region at which the value of x is allowed, in this case the radical function. And then that equals to 2. And what about 1? F of 1. Where is 1 allowed? Oh, hold on. Need to be careful over there. What is f of 1 equal to?
It's not equal to.
Not equal to, oh, I mean, x equals to 1? Yes.
Well, wouldn't it not appear in either technically?
Yes, exact. That is correct. However, there's a word for that. Well, we're not solving an equation, but you're getting close. I think you get the right idea. I'll give you a hint. Starts with a U.
Undefined.
Undefined. All right? Undefined. Now, what about, okay, let me make up another one. F of negative 6. Okay, f of negative 6. How would that be?
Undefined.
Undefined also, do you see any graph for x equals to negative 6? We don't see any points for at that value of x. That's also undefined. All right. And let me put it here real quick. All right. All right. Domain. Okay, the domain of this function. I'll let you work on that one for a couple of minutes. Okay, domain and range for this function. Well, again, the domain. To get the domain, we need to scan the graph from left to right. So, notice the leftmost value of x, and well, you need to be very careful here because some of you somehow interpreted this part of the graph as if it had an arrow, which in reality there's no arrow there. All right, that just ends up at a value, at a solid value that is exactly -3. So when we scan the graph from left to right, that means we start at -3, we go through this hole, and then yes, we go to -infinity. And so we need to break up this arrow. I know that arrow for the radical function looks like it goes flat, but trust me, it goes increasing in the y direction. Maybe not as fast as it's going increasing in the x direction. So it is safe to simply break the arrow up into two portions here. And yes, this is going to mean -infinity. In order to describe that, well, that'll be -3 with solid -3 to 1, and then union 1 to infinity, right? And in this case, that's how we're going to exclude that one that is part of the whole. Now, for the range. And again, the range might be a little bit deceiving, you know? It might be a little deceiving because, well, this arrow right here for the radical function, which again doesn't seem like it's going to go forever in the y direction. Actually, this green point right there seems like that's a larger value, but no, it's actually this going all the way up to positive infinity. So scanning the graph from bottom to top, the smallest value of x is -1. It's +1 rather. However, notice what we have at y equals to 1. We have an open circle, right? That means it is not part of the domain. So then number 1, start at -1 and simply go all the way to positive infinity, and make sure to put parentheses for -1. Now, how do we express these two, the domain and the range, using set builder notation? Because again, we need both notations. That is, so that's interval set x such that, okay, write this guy in inequality form, that is -3 -3 less than or equal x less than or equal 1, comma x greater than 1. Essentially, just copy these two inequalities, right? That's pretty much. And for the range, this one is a lot simpler to do. That is y such that y is greater than oh, not -1, actually +1. I don't know where that -1 came from. So 1. All right? And that's how we get the domain and range for this function. All right? You know, just because. All right, okay, let's see if this graph is either even or odd or maybe neither. So why not? Why? No symmetry at all, right? So there's no symmetry about the y-axis. There's no symmetry either about the x-axis. So, yep, that's true. Yep, I'll take it. Oops, change color. Neither, all right? And well, let's see about, okay, F, G, increasing. What are the intervals, or what is the interval at which the function is increasing?
Parentheses 1 to infinity.
Parentheses 1, comma infinity, that's correct. Increasing for 1 to infinity. How about decreasing?
Bracket negative 2.
Okay, bracket -3,
1 parentheses.
1 parentheses, that's correct, all right? From -3 to 1, inclusive, exclusive, respectively. That is correct. Is there anything else we did? Well, so about a maximum or a minimum. Well, oh, do we have a maximum? Do we have a minimum? Yes.
We have a minimum, but not a maximum.
We have a minimum. Well, what would be the minimum?
1.
However, do you see that that is an open circle? So there's really no point in there, all right? Even though, yeah, I agree, because it's going down the hill and then up the hill. Yes, that's the behavior we need to see on a graph to determine that we have a minimum value, but because of the open hole, there's no max and minimum. There's no minimum. I mean, that's not a minimum. What about maximum? What is that? Infinity. What tells us the maximum is infinity, essentially?
Keeps rising.
Keeps rising all the way.
To infinity on the right side.
All right, but okay. Now let's think of it differently. Well, we've been discussing how infinity is not a number, right? So infinity is just an idea to describe something that gets bigger and bigger and never ends. However, let's think of it as if it were a number. Infinity is this, boom, whatever that is. So we can think of that infinity as an absolute maximum, right? Okay?
Well, you would have a local maximum.
What is that local max?
5.
5, right? So we have a local max. So if I, well, let me okay, minimum, maximum, okay, no minimum, no minima values, And how about relative max? That is at okay, the y value is max, but in this case that maximum or minimum, even though in the previous exercise we express it separately, occurs at x, and the maximum is whatever the y value. We can simply express it using the order pairs. What is it? -3 to 5, -3, 5. So that's fine, as order pair is fine. All right. I don't think I think that's pretty much what we analyze of a function so far, right? Okay. Okay, so example number 3, we have this crazy looking piecewise function. It doesn't have just 2, but actually 4 pieces, and even the conditions are as crazy. Well, let's see. So number 1, we have the square function that is x squared between 0 and 2, excluding the endpoints. Yes, when we create the table of values, we will still evaluate them at 0 and at 2, but just keeping in mind that those points that we obtain out of them are going to be represented as wholes. All right? Now, let me use one color to highlight that piece right here. And I'm going to use that same color to create the table and get the points. So x, y equals to x squared. So we're going to do 3 points, 0, 1, and 2. So that's a 0 squared, 1 squared, and 2 squared. That equals to 0, that equals to 1, and that equals to 4. That's going to give us the order pairs x, y, 0, 0, 1, 1, and 2, 4. And on the one hand, well, that's going to be whole. I'm just going to write down, well, I'm going to write the whole word. Whole, solid, whole. Why whole, solid, whole? Well, whole because it's less than only, greater than only for 2. I mean less than rather. So, so in this case, well, that'll be whole. Everything in between will be solid points. Let's plot those points. So, well, that'll be the point 0, 0, the origin as a whole, 1, 1, and then 2, 4. That actually a whole. And that's going to look like only a portion of the parabola, not the whole parabola, but actually like with open circle or open bubble endpoints. All right. So that's the first part. The second part, let me use a different color, yellow. Let me use yellow for this. Whoops. So x plus 2, that'll be then, okay, yes, yellow, so that is x, and then x plus 2, and oh man, y equals x plus 2. So we get the y value in accordance with the rule y equals to x plus 2. All right, however, check the condition. In this case, x plus 2, that is all the only input value that we can do are only from 2 to 5. But again, we're going to exclude the endpoints. Yes, we are still going to substitute those values, but keeping in mind again that those are going to be open circles. Those are going to be holes. 2, 3, 4, and 5. So that is order pair 6, y. And well, that is 2 plus 2, 3 plus 2, 4 plus 2, and 5 plus 2. That equals to 4, 5, 6, and 7. That's going to give us the order pairs 2, 4, 3, 5, 4, 6, and 5, 7. And again, the endpoints 2, 4 and 5, 7 are wholes. How do we know those are wholes? Well, that's because of the inequality symbols in the condition. Let me scroll it up a little bit. Notice how we have just the greater than only, less than only, without the equal. If we had the equal part, then we would put solid points. Everything else in between, however, those are solid. All right, let's plot these order pairs. So that'll be, okay, with yellow, that's 2, 4, 3, 5, solid, 4, 6, solid, 5, 7, open circle. All right, so that's the second part. All right, f of x equals to 7 for x greater than or equal to, what's that, 5? Okay, let me use a different color. Let me use purple. 7, okay, for values of x equals to greater than or equal to 5. Well, that f of x equals to 7, it's one of those constant functions. It's a horizontal line. So technically, that should be the following line, this horizontal line at y equals to 7. However, we don't want the entire line in here. Otherwise, well, notice how in some places the vertical line test would fail, and that will not be a function anymore. So that'll be only for x greater than or equal 5, which in this case, that point, that equal to 5, fills in the hole in here for the yellow part. And lastly, that last part of the piecewise defined function, that might be a little weird. So f of x equals 5 for x equals to 2. So that is when x equals to 2. Oh, yes, another color. So for this means when x equals to 2, y equals to 5, because f of x equals 5. And again, f of x is the same as saying y. So that's going to be a single order pair when x equals to 2, y equals to 5, which will be this point, like in the middle of nowhere. Yes, these are very common functions with, curves and then lines and other things, and also with points like in the middle of nowhere. That is correct. All right, let's see what else do we have. What's next? Okay, so looks like we're done graphing the piecewise function. Now let's analyze it and compute some function values. Oh, by the way, I forgot something, a little detail that actually means a lot. This one is an arrow here. All right, the purple part is an arrow. All right, so let's go to the bottom part of the grid here and answer the questions. F of 3. So here, in this case, we need essentially 3 sections. So is 3 allowed in the green section, the yellow section, or the purple section? Which one? Yellow. So f of 3, that is the y value when x equals to 3 equals to, that equals 5. All right. What about f of 1? Where is 1 allowed in the green section, the yellow section, or the purple section? In the green section. And f of 1 equals to also 1. What about f of 2? Apparently undefined. Well, we see a hole in there, right? But we still have that point in the middle of nowhere where, yes, so check this out. When walking along this curve right here, yes, we're going to walk. Yes, we would have to jump, but we can still stand in here, right? So the function is still undefined. I know it's weird to have a function that is undefined at a point in the middle of nowhere, but it's still defined at that value. So in this case, the y value is going to be 5. What about f of negative 2? Green section, yellow section, or purple section, or that dot in the middle of nowhere? Undefined because there's no section for negative values this time, right? So, undefined. Undefined it is. All right, domain. Okay, let's look at the domain. That is, again, scan the graph from left to right. And I know this one I can already see it's gonna be a little tricky, but well, you'll see. You'll see how it's gonna work. Any ideas as of the domain?
So, I don't know, I haven't included the solid dot, but I tried. So it should be like parentheses 0, 2 parentheses, U, I assume brackets 2.
That's where it gets tricky, right? So, and the reason why it gets tricky, it's because that point is somewhere else, all right? So, you know what? Let's, in this situation, let's just pretend that this point is covered here, because I mean, whether that point is here, there, or there, or there, I mean, the value of x equals to 2, it's still an okay input for the function, regardless of what the y value, the output is. So, in this case, we can go about just from 0 all the way to infinity. No problem. 0 excluding the 0 all the way to infinity, and using the set builder notation, that is x such that x is greater than 0. What about the range? All right, that might be a little trickier, maybe not. What do you think about the range? Hmm?
From 0 to 0?
From 0 to... Well, okay, that's good to begin with. 0, why not? I'll take it. 0, and also with parentheses, because yes, scanning the graph from bottom to top, yes, the lowest value is 0, however it's an open circle, so we need to exclude it somehow. How? With parentheses. Yes.
So for this one, the dot would not apply, so it'd just be 4 parentheses, and then U, it'd be 4 parentheses.
That is correct.
7 parentheses, and then U, bracket 7.
That is correct. So in this case, to look at the graph from bottom to top, we go in this case, okay, the lowest value, which is 0, yes. Excluding, then go up, scan to the top, okay, yes, no problem, no problem, no problem, until we get to x equals to 4. Oh, there's a hole in there. Keep going up. Doesn't matter with this dot in the middle of nowhere, because it's either here or there, so that doesn't matter. So keep going all the way. Oh, the maximum value in this case is, yes, 7. So that is 0 to 4, and then union 4 all the way, not to infinity, but to 7, and in this case with bracket. And this one we can express using set notation, that is y such that y varies between, what's that, 0 and 4, and then 4, oh, y varies between 4 and 7, or rather, nope, less than or equal to 7, like this. All right. Let's see, what else can we do about this guy? Maybe, what time is it? Okay, we're good. Let's make up letter G. Yes.
Why did we ignore the open circle for the domain, but chose to like pay attention to it in the range?
Okay, because for the domain, when scanning the graph from left to right, yes, we see a hole, right? However, that hole is in a way covered by that point in the middle of nowhere. Yes, it's not covering the hole, but I mean, the input x equals 2, it's still okay, despite it's not making it, it's not giving us a smooth curve in this case, all right? But in this case, when we scan it from bottom to top, well, that is, well, you can look at this from the side, and then in that case, the hole is not filled in the y, when we look at it in the y perspective, right? So even, odd, neither, which of the three? Neither. No symmetry at all. Okay, Increasing. Increasing.
Parentheses, 0, 7 brackets.
Uh-huh. Well, actually the same as the domain, right? The same as the domain. It's increase. Oh, wait, hold on. Oh, not to 7. So it's in the x direction from 0, and then increases all the way to actually 5 before it gets flat, right? So 0 to 5. Well, let me change this to blue. And then let's see. I. Decreasing. Is this graph decreasing at all?
No.
So in this case, simply NA, not applicable. J, constant. That is intervals where it's neither increasing nor decreasing. I think this graph is featuring that, right? So
It would be 5 to infinity.
5 to infinity. From 5 to infinity, all right? And in this case, well, parentheses for 5. Is there anything else we did about it? Maximum and minimum values, well, there's no minimum value, I mean, like legitimate minimum value had we had, otherwise a solid point over here, that would have been the minimum value. However, the maximum value, it's weird to think about a maximum value because the maximum value is y equals to 7, but for which values of x? The way we will define, so j, k, maximum, no minimum. Well, I'm not going to list the minimum because there's no minimum at all. So that'll be, the maximum is y equals to 7 for all x greater than or equal to 5. Right? Actually, there's a symbol for this. It's an upside down. An upside down A means for all. Right? Just to get into more formal symbols, upside down uppercase A means for all. And then there's another pretty cool symbol. It's a backwards E, like this, that means there exists. Well, we're going to look at this later in the semester. At least we can go with the for all for now. All right.